Scroll through social media today, and you will see perfectly fluid machines seamlessly folding laundry or navigating crowded subways. But step onto an actual factory floor, and those bipedal machines are largely absent. Most industrial operations rely on simple, wheeled autonomous mobile robots, or AMRs, because they are cheaper and highly reliable for repetitive tasks. The flawless general-purpose robots we see online rely on technological crutches hidden just out of frame, ranging from tightly choreographed scripts to remote human operators. As of May 2026, the humanoid industry is essentially in its Netscape phase. The foundational technology is built, but seamless everyday utility is still years off. Confusing marketing demos with industrial reality ignores three massive engineering hurdles holding back mass deployment. The first hurdle is autonomy. Many impressive viral demonstrations use teleoperation, where a human operator wearing a motion capture rig controls the machine's every move. When robots attempt tasks independently, they run into the long tail problem. They function fine in familiar environments, but immediately freeze or fail when they encounter novel, unexpected scenarios not in their original training scripts. This happens because processing raw sensory input and calculating the correct physical response takes too much time, creating a processing lag that paralyzes the machine. Software developers are tackling this latency right now. Meta's new Muse Spark model uses a technique called thought compression, which streamlines how AI processes sensory data and logic to eliminate that hesitation. Closing the autonomy gap requires robots to stop mimicking pre-programmed human motions and start thinking through physical logic in real time. Current models download skills inside pristine digital simulations, executing actions perfectly across frictionless environments. But a perfectly calculated step unravels against dust, irregular floor textures, or messy workspaces. These unpredictable elements overload the system in the physical world, causing total failure. To bridge this gap, research centers like the Fujitsu-CMU Physical AI Center are developing world models. These are internal physics simulations that allow a robot to predict a physical outcome, like understanding a glass will shatter if dropped, without actually having to experience it first. True physical autonomy means embedding the actual laws of physics directly into the robot's brain, rather than relying on millions of frictionless digital trial runs. The third hurdle is mechanical. An industrial arm has 6 joints. A humanoid requires over 30 joints and 50 motors. This massive mechanical load, combined with running high-end AI on board, creates an immense power draw, capping most robots at 4 hours of use. We are beginning to see hardware solutions in 2026, specifically new energy-efficient memory chips designed to handle local AI processing without immediately draining the battery. Even with perfect software, a robot cannot replace human labor if the machine is mechanically fragile and unable to survive a standard 8-hour shift. Right now, mass adoption is restricted to the pilot phase. Companies like Hyundai and BMW are testing robots on specific dull and dangerous jobs under highly maintained conditions. Expanding beyond these limited trials requires solving the hardware limits, but it also requires writing the missing safety standards for heavy machines operating in close proximity to human workers. This timeline projects the 10-year trajectory required to clear these friction points. Combining thought compression, world models, and energy-dense silicon compounds the technology. By 2036, these advances should phase out teleoperation entirely, close the sim-to-real gap, and extend battery life for uninterrupted factory shifts. The viral clips we watch today bear little resemblance to the quiet, grueling trial and error occurring daily on factory floors. General-purpose robots will arrive, but not through a sudden software update. It will take 10 years of painstakingly teaching digital brains how to survive in the